When determining the appropriate wire size for a 1600 amp feeder, several factors must be taken into account. Firstly, load requirements, secondly, voltage drop, and thirdly, conduit fill and bending radius. Let's evaluate the proposed solution of 4 500 km copper THHN conductors in 4 3-inch conduits. The wire size must be sufficient to carry the expected load current without exceeding the allowable ampacity. The wire size should also minimize voltage drop to ensure that equipment receives adequate voltage. Additionally, the selected wire size must fit within the conduits while maintaining the proper bending radius. To perform a thorough evaluation, we will go through a series of calculations. Firstly, we'll consider the load current. Assuming a load of 1600 amps at 480 volts, we should confirm that this voltage is a line-to-line or line-to-neutral measurement. With a 480 volts Y system, the line-to-line voltage is 480 volts. For this example, we can skip the calculation shown because the load current is directly stated as 1600 amps. Secondly, we need to determine the allowable ampacity. For 500 km copper THHN conductors in a 3-inch conduit, the allowable ampacity is approximately 400 amps per conductor, based on the National Electrical Code, (NEC) tables. These tables provide ampacity ratings for various conductor sizes and insulation types under specific conditions. The NEC should always be consulted for the most accurate and up-to-date information, considering directing factors for ambient temperature and the number of conductors in a raceway. The NEC specifies that for conductors rated 600 volts or less, such as THHN, the ampacity shall be determined using NEC Table 310.15b16, formerly Table 310.16. This table lists ampacities for conductors insulated with different materials e.g. THHN, THWN based on conductor size and temperature rating when installed in a raceway or cable or directly buried in earth. The table ampacities are based on an ambient temperature of 30 degrees Celsius 86 degrees Fahrenheit. If the ambient temperature is higher, a correction factor must be applied as specified in NEC Table 310.15b2. Furthermore, if there are more than 3 current-carrying conductors in a raceway or cable, the ampacity must be derated according to NEC Table 310.15 current. This derating accounts for the increased heat generated by multiple conductors in close proximity. For example, if there are 4 to 6 current-carrying conductors, the ampacity must be derated to 80% of the table value. If there are 7 to 9 conductors, the ampacity must be derated to 70%. The NEC also provides specific requirements for conductor installation, including conduit fill limitations and bending radii. These requirements are intended to ensure safe and reliable operation of electrical systems. Exceeding the allowable ampacity can lead to overheating of the conductors, insulation damage, and potentially electrical fires. Therefore, it is crucial to select a conductor size that can safely handle the anticipated load current, considering all applicable derating factors and installation requirements. In this scenario, with 4 500 km THHN conductors, each rated at approximately 400 amps, the total ampacity would be 4 times 400 amps, equaling 1600 amps. This matches the feeder requirement, but it's crucial to confirm that all derating factors have been applied. Thirdly, let's examine voltage drop. To calculate the voltage drop, we can use the formula voltage drop equals load current divided by conduit ampacity, multiplied by length, multiplied by conductor resistance. This formula is a simplification and may not be suitable for precise calculations in all scenarios. More accurate voltage drop calculations may require considering factors such as conductor reactance and power factor. Accurate voltage drop calculations are essential for ensuring that electrical equipment receives adequate voltage, especially in long circuits or where voltage-sensitive equipment is used. The NEC recommends limiting voltage drop to no more than 5% from the source to the farthest point of utilization. Excessive voltage drop can cause equipment malfunction, reduced efficiency, and premature failure. Let's assume a conduit length of 100 feet and a conductor resistance of 0.35 ohms per 1000 feet. The voltage drop would be calculated as follows: voltage drop equals 1600 amps / 1600 amps multiplied by 100 feet multiplied by 0.35 ohms / 1000 feet, which equals 0.35 volts or 3.5 millivolts. This calculation needs to be reviewed. The load current used in the voltage drop formula is typically the actual current flowing through the conductor, not the total load current of the feeder. Also, the conduit ampacity is not a relevant factor in the voltage drop calculation. A more appropriate formula for calculating voltage drop in a single-phase circuit is voltage drop equals 2 times current times resistance times length divided by 1000. For a three-phase circuit, the formula is voltage drop equals square root of 3 times current times resistance times length divided by 1000. In these formulas, current is the current flowing through the conductor in amps, resistance is the conductor resistance in ohms per 1000 feet, and length is the one-way length of the conductor in feet. Let's recalculate the voltage drop using the three-phase formula, assuming a balanced load. In a balanced three-phase system, the current is evenly distributed among the three phases. Therefore, the current flowing through each conductor would be the total load current divided by the square root of 3. Current per phase equals 1600 amps / square root of 3, which is approximately 923.76 amps. Using the three-phase voltage drop formula, voltage drop equals square root of 3 times 923.76 amps times 0.35 ohms per 1000 feet times 100 feet divided by 1000. Voltage drop approximately equals 5.6 volts. To express this as a percentage of the supply voltage, we divide the voltage drop by the supply voltage and multiply by 100. Percentage voltage drop equals 5.6 volts / 480 volts times 100. Percentage voltage drop approximately equals 1.17%. A voltage drop of 1.17% is generally acceptable, as it is well below the recommended limit of 5%. However, it is essential to consider the cumulative voltage drop throughout the entire electrical system. If there are other voltage drops upstream or downstream of this feeder, the total voltage drop may exceed the recommended limit. Finally, let's consider bending radius. The minimum bending radius for 500 km copper THHN conductors is typically specified by the manufacturer and is also addressed in the NEC. A common recommendation is 12 inches. Ensure that the conduits provide adequate clearance for the wires to be bent without damaging the insulation. The NEC provides guidelines for conduit bending radii in Article 344 for rigid metal conduit, Article 348 for electrical metallic tubing, and other relevant articles for different types of raceways. The minimum bending radius is typically expressed as a multiple of the conduit diameter. For example, the NEC may require a minimum bending radius of 6 times the conduit diameter for certain types of raceways. The purpose of specifying a minimum bending radius is to prevent damage to the conductors during installation and to ensure that the conductors can be pulled into the conduit without excessive force. Sharp bends can damage the conductor insulation, reducing its ability to withstand electrical stress and potentially leading to short circuits or ground faults. The minimum bending radius for conductors themselves is also specified in the NEC, particularly in Article 300.34, which addresses conductor bending radius. This section requires that conductors be bent so that the insulation is not damaged and the conductor is not overstressed. The specific bending radius requirements depend on the size and type of conductor, as well as the raceway or cable in which it is installed. In summary, based on these considerations and assuming that the calculations are reviewed and verified by a qualified electrical engineer, for 500 km copper THHN conductors and for 3-inch conduits could be a suitable solution for supplying a 1600 amp feeder to the office. The wire size provides sufficient ampacity, minimizes voltage drop, and meets the bending radius requirements, provided that all NEC guidelines and manufacturer specifications are followed. It is important to consult the NEC and local electrical codes for specific requirements and to ensure compliance with all applicable regulations. Remember that this analysis is based on the information provided and should be verified by a qualified electrical engineer. Factors such as ambient temperature, conductive bundling, and specific equipment requirements can affect the final wire size selection.